In today's video, we're going to talk about neutralization reactions, which is a class of chemical reactions where an acid reacts directly with a base to form products. Now, this is a class of reactions that you've already encountered in Chapter 4 from last semester, so we're going to start off with a review talking about the types of products we can predict and expect from a neutralization reaction between a strong acid and a strong base. We're next going to turn to something that's a little bit more Chapter 14-esque, talking about acid-base reactions in the context of equilibrium, and for that, we're going to talk about how we can predict the products when instead it's a weak acid reacting with a weak base. And we're going to be able to quantify this a little bit and be able to predict whether the reactions between a weak acid and a weak base will be product-favored or reactant-favored, and how we can calculate those equilibrium constants. So with that, let's go ahead and get started with a little bit of review of Chapter 4. We talked about in last semester how if you have an acid and a base that react together, and I've labeled my acids in orange, my bases in blue, and you'll notice since we're talking about strong bases are always a cation plus hydroxide. So I labeled them BOH, but you can see some examples in blue like sodium hydroxide or cesium hydroxide. And because all of these strong bases are hydroxide, the products of all reactions between strong acids and strong bases are always water and a salt. And to help you keep track of where the hydrogens and oxygens are coming from, I color-coded it. Of course, when we write the chemical formula for water, you almost always write it as H2O rather than HOH, but it's the same number of hydrogen atoms and the oxygen. As for the salt, that's going to depend on what specifically is the cation from the base and the anion from the acid. And so let's go ahead and do a couple of examples. So our first example, we've got HCl plus sodium hydroxide. That means that chloride is our anion, sodium is our cation, and so that's going to give us products that are always water, plus, in this case, our salt is going to be sodium chloride. Looking at our second example, once again, this one has our anion in this case is going to be SO4, and in fact SO₃², which is sulfate. So it's going to be sulfate, and cesium. We want to be a little bit careful because while our products are still water and a salt, we want to make sure that we get the right chemical formulas that have our salt with balanced charges so that it's overall neutral. And that means that we need to think a little bit about how this cesium, because it's in row or group 1 of the periodic table, is going to have a +1 charge. Our sulfate is going to have a charge of -2. And that means that the chemical formula for our salt should be 2 cesiums and 1 sulfate so that we get a balanced chemical compound. And then last but not least, the other reason I wanted to give this example is because you want to make sure whenever you're predicting the products of a reaction that you actually give a balanced chemical equation. And so for this, since I've got 2 cesiums, I'm going to need a 2 in front of here, and then so that my hydrogens are balanced, it looks like I also need a 2 in front of my water. Okay, so that's neutralization when it comes to strong acids and strong bases. Hopefully fairly boring review for us, but I wanted to present it just in case we're a little rusty on our Chapter 4 context. And for this section, I would say we should have one qualitative takeaway, which is that now that we're in Chapter 14, we can finally talk about what we meant by neutralization this whole time, and it's specifically talking about the resulting pH that we would expect of these products. Because while our strong acid by itself, like HCl or H2SO4, is going to have a pH that is much less than 7, and usually for really strong acids, I would say you're going to have a pH probably close to 1, maybe less than 1, something that's like a little bit risky to human health. And similarly with our strong bases, you're going to have a pH that's much greater than 7, maybe something around 13 or 14. Again, not something that you want to be risking getting into close contact with. When we react together, a strong acid and a strong base, the salt and the water, those are just neutral compounds that don't have anything other than a pH of 7. And so we call it neutralization because these reactions result in a pH neutral solution. Okay, So let's go ahead and talk through what's going to be different, what's going to change when instead of working with a strong acid and a strong base, we start to work with weak acids and weak bases. Well, a lot of the formula is going to look pretty similar in terms of the acid. Most acids are still just some compound with an extra proton attached that can, leave off and dissociate. But weak bases are not hydroxides. They're just other compounds like ammonia or carbonates or bicarbonates. And so you typically out of these reactions don't get water as one of your products, but instead what you're going to get is you're going to get whatever the conjugate base is of your original acid, that's shown in green, and you're going to get the conjugate acid of whatever base you started with. And so we can give a couple examples of this as well. We'll start off with two pretty common acids and bases. We've got acetic acid and we've got ammonia, and I've drawn their Lewis structures over to the right. And so if we're trying to predict the products of this, I think it's helpful to do it both in terms of the chemical equation as well as thinking a little bit deeply about what's happening with these Lewis structures. And so looking at our template, it looks like the conjugate base of acetic acid is going to be the same compound, but we need to get rid of a hydrogen. And we'll talk about this later on in this chapter, why I've chosen to remove the hydrogen that was next to the oxygen atoms rather than one of the three hydrogens that was next to a carbon atom. But what we're going to learn a little bit later on in the chapter is that this hydrogen right here is the acidic proton, or it's the one that's going to leave if you're involved in an acid-base reaction. For our other compound, NH3, we need to have, if the product of this reaction is going to be its conjugate acid, and the conjugate acid of NH3 is NH4+. And so in terms of thinking about our Lewis structures, what's going to happen is this proton is going to leave and be bonded to our ammonia. And so the products of the reaction are going to be simply the same compounds, just we've traded off where the hydrogen belongs. It originally belonged to the acetic acid, now it belongs to the ammonia, and that gives us our two products, which are called acetate and ammonium. All right, so let's go on to our second example. We've got SO₃², our sulfate, and we've got bicarbonate. And I wrote the reaction in this order. Hopefully you didn't get tricked, but we don't always write things in the order acid, then base. And in fact, in this case, the only hydrogen that we have to act as our acid is going to be the one on the right. So we need to be a little bit careful there. And then we've got our sulfate, that's going to be able to accept a proton. And so once again, we're just trying to predict products, which means we need to think about what is the conjugate acid of our base and what is the conjugate base of our acid. And so in that case, the products we're going to end up with is one, we're going to get the sulfate is going to turn into bisulfate. So it's going to pick up a proton, and it's going to get more positively charged by 1. So it'll go from a 2- to a 1- charge. And then our other product is going to be carbonate. And carbonate is going to have the chemical formula where it's losing hydrogen and it's losing a positive charge, so it's getting a little bit more negatively charged. And that's going to give it the chemical formula CO₃². Okay. And that is pretty much it when it comes to talking about neutralization reactions for weak acids and weak bases. Oftentimes in these problems, though, when it comes to weak acids and weak bases, we can go one step further and we can talk a little bit about if these compounds represent, because it's weak acids and weak bases, it's going to represent reversible reactions at equilibrium. We can talk a little bit about, well, where is equilibrium? For these two different reactions, does equilibrium lie to the left, to the right, or smack dab in the middle? And so the next thing that I want to show you all is how we can use Ka and Kb values for these different acids and bases in order to quantify where equilibrium is going to lie in terms of neutralization. And so in order to talk about that, we've already in this pre-class assignment been talking a fair amount about coupled equilibrium. And so I want to show you first and foremost that we can think about these types of neutralization reactions as a coupled equilibrium problem. And the reason we're going to do this is because if you look in your textbook or common internet sources, K values for neutralization reactions are almost never reported. But on the other hand, Ka values and Kb values for various compounds are very commonly reported. And so to remind us, whenever we're talking about Ka, it's always the reaction of an acid plus water gives rise to a conjugate base and hydronium, H3O+. And so in terms of our reaction, the two acids we've got in our generic form of the expression is we've got Ha and we've got Hb+. So if we write down the Ka expressions for both of those, and I've got both in terms of equation, in terms of the K value, you might notice that there's actually a lot of similarities between what's shown there and what's shown if I write down the K equilibrium expression for the neutralization reaction itself. And you should take a minute to confirm that this K equilibrium expression, it didn't come from nowhere. It's just our normal products over reactants. We don't have any coefficients, so we don't have to have any exponents. But for this K equilibrium, it looks awfully similar, almost like it's a combination of these two reactions right here and their associated K equilibrium values for these Ka expressions. And mathematically, what we can notice is that they're basically the same. The only thing that I need to do in order to get these H3O+ to cancel and make sure that the Hb+ shows up in the numerator is I just need to take my Ka value for the first reaction and then also multiply it by the Ka for the second reaction. But before I do that, you'll notice in order for the H3O+ to cancel and for the numerator and the denominator to look correct, I probably need to flip or take the reciprocal of this reaction. And so in order to get back to the original K expression we were looking for, it turns out that that is equal to Ka, the acid dissociation constant for Ha, our acid reactant, divided by Ka for Hb+, which is another way of saying that whatever the conjugate acid is for your base that you start with, that's where we get that value from. And I just want everyone to see that if I plug in the two different expressions that I have, here's Ka for our acid, here's Ka for the conjugate acid of the base we started with, then our H3O+'s are going to cancel out beautifully. We'll be left with this expression shown here, and lo and behold, that is exactly equal to this K equilibrium value that we were trying to get to. And so the rules of coupled equilibrium tell us that if you want to find K for a neutralization reaction, really there's only two things that you need to look up. You need to have in hand the Ka value for the acid that's part on the reactant side, and then you also need to have the Ka expression for the conjugate acid that's on the product side, or put differently, the conjugate acid for whatever is the base that you started with. Okay, so we're dealing with a lot of different acids showing up, so I think this is best worked out with a couple of concrete examples. So let's go ahead and go back to these original two reactions that we were predicting the products for, and I went ahead and wrote down all of the information that I was able to glean from our textbook, and so you can see we don't get Ka and Kb values for everything on this list, but you'll see that we have enough that we can work with this. So the first example that we've got, I was able to find Ka values for both bicarbonate and bisulfate, and you can see what those numbers are. And so what we want to do to predict our overall K value is K is going to be equal to, again, we're looking for the numerator should be the acid that's on the reactant side, which is going to be HCO₃-, and then our denominator should be the acid that's on the product side, which is bisulfate. Plugging in our numbers, we're going to get that this is equal to 4.7 times 10 to the negative 11th divided by 1.2 times 10 to the negative 2. And if we go ahead and pull out our trusty calculator, that is going to be equal to equals 3.9 times 10 to the negative 9th. And so if you're asked to compute a K value for a neutralization reaction, that's all that we have to do. Oftentimes you'll also be asked to interpret the K values. And so in this case, notice that the exponent, -9, means that this number is way smaller than 1. And so qualitatively, we could say that this means that the reaction is very reactant favored, meaning that equilibrium lies very far to the left-hand side of this equation. Or, in more practical terms, it means that if I put together a mixture of sulfate and bisulfate and bicarbonate and carbonate and let it sit for a little bit, when it gets to equilibrium, in my flask, I'm going to have almost entirely sulfate and bicarbonate and just a teeny tiny bit of bisulfate and carbonate, these two products present. Okay, so that's one example. The second example is a little bit trickier because notice I was not able to find in the textbook any information about the Ka value for ammonium. And the good news is this isn't actually that big of a deal because remember, you just learned that whenever you're trying to relate together a Ka value and a Kb value for a conjugate acid-base pair, we simply have to keep in mind that the product of the Ka and the Kb value for that conjugate acid-base pair is going to be equal to Kw. And so that means in our case, Kw is, we're going to assume we're at room temperature here. So that means that Kw is 1 times 10 to the negative 14th. And so our Kb value for ammonia is 1.8 times 10 to the negative 5th. And solving for Ka, that's simply going to be Kw divided by Kb. And once again, doing this in our calculator, we're going to get 5.6 times 10 to the negative 10. And so we can go ahead and plug in Ka for ammonium is going to be equal to 5.6 times 10 to the negative 10. And so now that we've done that little cute trick so that we can go translate between Ka and Kb values, now we can go ahead and calculate our overall equilibrium constant for this neutralization reaction. Just like before, we're going to be plugging in Ka for the acid that shows up on the reactant side, which is acetic acid. And then in the denominator, we're going to plug in the acid dissociation constant for the acid that shows up on the product side, which is ammonium, and plugging in the numbers that we just calculated. In this case, we get a very positive number, 3.2 times 10 to the 5th. And so this tells us that this neutralization reaction is very product favored because this number is way bigger than 1. Okay. So that's all the content we were hoping to get through for this segment. I hope you've learned a couple of takeaways when it comes to dealing with neutralization reactions. Again, when we're talking about strong acids and strong bases, you can always expect that one of the products is going to be water, the other product is going to be a salt. And because these are strong acids and bases, we consider them to be irreversible reactions. With weak acids and weak bases, it's actually a reversible reaction. You should always draw that equilibrium arrow. And the products are going to be whatever the conjugate bases and acids are of your original reactants. And then something that we didn't reinforce, but I hope you started to notice, is that when we're talking about neutralization reactions, regardless of what type of, whether it's weak or strong, equilibrium is always going to favor the side of the reaction that has the weaker acid. And so I would encourage you to think about this in terms of chemical stability. When we say stronger acids and stronger bases, it's a little bit of a misnomer. I think it's better, more chemically reasonable to think about those as being more reactive. And so more reactive, less stable acids and bases like to disappear, and they like to turn into more stable versions of themselves, which we call weaker acids and weaker bases. And so equilibrium is always going to favor whatever's the more stable side of our reaction, and the more stable side is always going to be whichever side has the weaker acids and bases present. All right, that is all. See you in class.